In this video, I will discuss the estimation of errors that we're making when numerically approximating certain integrals, even if we don't know how or what the exact value of that integral is. Now, before we start our study of the errors, I give just a brief overview again of the integration methods that we've seen in this lecture. And those integration methods, well, we've seen a number of Newton-Cotes methods in which the function to be integrated, or the integrand, was replaced, let's say, or approximated by a polynomial of degree n on the interval ab. And if n is 0, well, then that polynomial is a constant. That's just a constant line, rectangular midpoint method. If n is 1, then we have a line, or a line with a certain slope. So that's the trapezoid method. And then for n is 2 and 3, well, we have Simpson's 1/3 method and Simpson's 3/8 method, respectively. And we also discussed the Gauss quadrature method, and that in the Gauss quadrature method, the entire idea is to approximate this integral with a weighted sum of function evaluations. Also, we applied these methods to specific examples, and we were able to give at least qualitative impressions of how accurate these methods are. For instance, that the rectangle method seemed not so super accurate, whereas Simpson's methods and the Gauss quadrature method seem to be quite accurate. Now, in this video, we will discuss in a bit more, we will investigate a bit more this error and give some more quantitative statements about each of these methods. Now, let's start out with the midpoint integration rule, and we will do an error estimation for this midpoint integration rule. Just to recap, so for the midpoint integration rule, what we do is we approximate this function, so this black line over here, which we want to integrate from axis A to axis B. Well, we approximate it using the function evaluated at the midpoint at a plus b over 2. Since this is a function, well, this integral is very easy to evaluate, and that corresponds to simply that this constant function evaluation, which is the height of this rectangle, multiplied with the width of the integration interval, which is b minus a. So that we have this blue area, the area of the blue rectangle, as the approximation of the area below the curve over here. Now, what can we say about the error here? Well, let's first define this error. And well, this error is simply the exact value of the integral, which we in general do not know, because if we knew it, there wouldn't really be a point in doing this numerical integration, except if we're just looking at some toy problems. So this is the exact value of the integral, which is not known, minus the midpoint rule, which we can easily compute. So this brings us no step further actually to giving quantitative statements about the error, because we cannot evaluate this term, this first term here. Now what we can do is we can replace this function f of x with a Taylor series expansion of f around the point, around this midpoint, around the point x is a plus b over 2. So let's do so, and this gives us this Taylor series expansion of f of x around the midpoint. And we have here, well, the function evaluated at the midpoint plus x minus the midpoint times the first derivative at the midpoint plus 1/2 x minus the midpoint squared times the second derivative of f evaluated at some psi between a and b, where this psi is not known. But we know that there is a psi between a and b for which this holds, for which this is exactly equal to f of x. Now what we can do is we can, well, plug this into the expression here. We replace f of x with this Taylor series expansion. And that is what we do in this slide. So what we see is we have replaced f of x with this Taylor series expansion, and here we still have this contribution of this of the midpoint rule. So now this integral looks a bit more complicated than the one in the previous slides, but I will show you that this is an integral which we can actually evaluate because there's a lot of constants in here. There is no f of x in here anymore because this f of x was actually the difficult point that caused us to have to resort to numerical integration. But let's take a look at each of the terms. So this is the first term, the second term, and the third term that we have to integrate. And let's take a look at which of these terms drop out and which of them make an effective contribution actually to this error. So let's start with this first term over here. So this is a constant, and we know that after integration, well, a constant is just multiplied with the width of the integration interval. So this is what this term turns into after integration. And well, if we compare this term here to what our midpoint rule dictates, well, we see that these two terms will drop out against each other. So this term and this term will actually drop out against each other. So that's nice. Terms are dropping out, and we can get a hope of simplifying the expression for the error. Okay, that's good. So let's move on to the second term. What do we have here? Well, we have the first derivative of f evaluated at the midpoint, which is simply a number that's not dependent on x. So that's a constant when we integrate for x. So this is simply a constant. And what do we have here? Well, this is x minus a constant. And that's something we easily know how to integrate. So x minus a constant, that will be 1/2 times x minus that constant squared, evaluated at x is b and at x is a. So after integration, this term simply becomes the term in the blue box over here. And if we actually take a look here, well, the first term, that's b minus a plus b over 2. So that will be b over 2 minus a over 2. Over here we have, this will become a over 2 minus b over 2. So we see that the terms within the brackets are each other's negative, but after squaring, they will become the same. So you see that these terms will also drop out against each other. And if I'm going a bit too fast here, I invite you to just work through this with pencil and paper, but you will easily see that these two terms drop out. So this here we have 0. So this entire term in the blue box also drops out. So in the end, we are left with only this term over here. This term consists of 1/2 times the second derivative of f evaluated at some point between a and b. We don't know which point that is, but we know that it's not dependent on x. So this is a constant. So 1/2 f double prime, that's a constant. And then here we have x minus another constant squared. So also that is something we easily can integrate. And what that becomes is, well, this will be 1/3 times this term between the brackets to the power 3, evaluated for x is b and x is a. So that turns out to be this term here in the purple box. And we can simplify this term by working out these things in the brackets a little bit. And in the end, you will come out with this expression for the error. So this is a relatively simple expression for the error of the midpoint rule. And let's analyze this for a moment. So we see, well, we have a constant 1/24, which is not so important. We see that this is proportional to the second derivative of f evaluated at some psi between a and b. This also tells us that if this second derivative is 0 everywhere between a and b, that the midpoint rule would be exact. And that is actually very intuitive, because if that second derivative is 0, then f is either a constant, for which the midpoint rule is obviously exact, or it is a first degree or it could be a first degree polynomial. So a line with a constant slope. And for that, we can also find that you can also easily intuitively see that if f of x were simply a line with a constant slope, that this midpoint rule would be exact. So that is that. And also a nice observation here is that we have here the width of the integration interval, so b minus a to the power 3. So the error is proportional to the width of the integration interval to the power 3. And that actually means that if this integration interval is quite large, well, then this error will also be quite large. Yeah, that is basically what this formula is saying. So if b minus a gets bigger and bigger, well, this error will get bigger and bigger. So you should be cautious about applying the midpoint rule as a standard integration rule to integration where the interval is quite large. However, we've also seen that whenever we're dealing with large integration bounds, or a large integration interval, we can increase the accuracy by not doing the midpoint rule in one step as an approximation to this integral, but by using a composite rule. And so in this composite rule, well, we subdivide the total integration interval from a to b with we subdivide it into these smaller subintervals. These subintervals, well, we take a capital N amount of subintervals, and each of these subintervals has a width of h, where h is b minus a, so the total width divided by n. And so for each of these subintervals, well, we apply the midpoint rule to approximate the area below the curve on that interval. And that corresponds to, well, this over here. So we have the integral from xi to xi plus 1. That is the integral from here to here, let's say, if I were 1. And instead of f of x, here we have f evaluated at the midpoint between those 2 points. And again, here we have a constant. Integrating a constant is simply that constant times the width of this interval. So we end up with this thing over here. Okay, so let's turn to an analysis of the error here. And let's first look at the error for a subinterval with index I, let's say. Now, for such a subinterval, we can simply repeat exactly the same analysis as we did for the total midpoint rule. So for a single midpoint rule over a single interval, because the concepts are completely the same. And also here we would find that the error for such a subinterval is equal to the width of that subinterval, which is h in this case. The width is cubed. We have this factor 24. And then the second derivative, which is evaluated at some xi I between xi and xi plus 1. Now, we're not really interested in the individual errors for those subintervals. No, we're actually more interested in the total error. So the error that we get after adding all these subintervals together. And that error can also be simply written as a sum of the individual errors for every subinterval. So just plugging this thing in here, we can throw the constant outside of the summation. We find that the error is h cubed divided by 24. And then here we have a sum of n second derivatives. Let's see whether we can make a bit more further sense of this error here. We don't know a lot about all these individual second derivatives, but if we start adding more and more of those terms together, well, we should be able to try and get this sum out somehow, because if we increase the total amount of subintervals, well, this would probably also increase if f prime is somewhat uniform, but h would decrease. So let's try to make this a bit more concrete. Now we can do so by defining an average second derivative for all those intervals. And we can do so simply by defining this average second derivative, f double prime bar, as the sum of all those intervals, the sum of all those second derivatives in those subintervals, and dividing this by the total amount of intervals. That's the definition of an average. We can then just recast this formulation a bit and saying that this sum is equal to n times this second derivative. And then we find that, well, just plugging this over here, so n times this average second derivative is equal to this sum. So we find that, well, this is h cubed times n times the second derivative. But we know that h times n is equal to b minus a. So we can take one of the h's in this h cubed and replace this with b minus a. And what we then see is that the error that we find over here is, well, proportional to the total width of the integration of the integral that you want to compute. But there's not much you can do about that anyway. That's what your problem is telling you. But something we can control is this h over here. So this h is dependent on how many subintervals that we use. And we see that this error is directly proportional to h squared. So that means that this is a second order method. So if we are able to divide h with the factor, let's say 2, so we take twice as many subintervals, then the error will be decreased with a factor 4. That is what such a second order accurate integration method is. We could also do the same for all of the other integration methods, all of the other Newton Cotes integration methods, at least that we've seen so far, all of the other composite methods. In the textbook, there is a derivation of the composite rectangle method, and the derivation is completely analogous to what I've just shown you for the composite midpoint rule. So you can take a look at it, and what you will find is that the rectangle rule is first order. So if you decrease h by a factor 2, also the error will go down by a factor 2. You can do similar analysis for the composite trapezoidal rule, which also turns out to be second order, or both of the Simpson's rules that we've seen, both of which turn out to be fourth order actually. Now let's take a look at our example that we've already discussed in the previous videos as well. Just a brief recap. Well, we wanted to, it's about a decelerating airplane, and it could be translated, this problem could be translated into computing this integral. So computing the integral of this function, this ratio, from v is 40 to v is 93. And we can actually compute this integral by hand. If you do a substitution, then it turns out that this is at least rounded to 4 decimal digits after the decimal separator. This is 574.1494. That would be the exact solution. And we took a look at how each of the integration methods that we discussed worked for this case. And well, we limited ourselves to only these 4 digits after the comma. And from that, we said that, well, Simpson is more accurate than, let's say, rectangle, and Gauss is also very accurate. But let's now try to be a little more precise. So instead of looking only at the solution, let's take a bit more of a detailed look at what happens with many more digits after the comma. So what we do is, instead of looking at the solution, I will investigate what the error is. So in the next table that I will show, all of the entries of the table are basically what is now the entry of that table minus the exact value over here. So this is the error that we get with numerical integration versus the exact solution, which is rounded to 10 decimals. So I could go even further, but let's say that after 10 decimals, we say that the error is negligible. Okay, so let's take a look, for instance, left rectangle rule. And we see that the left rectangle rule, well, the standard left rectangle rule has an error of about 200. If we take 10 subintervals, the error is decreased by a factor of 10. If we take 100 subintervals, the error is again decreased by a factor of 10. So only very slowly this error goes down. If we were to try and get this accurate to 10 decimals, we would have to take, I think, billions and billions of function evaluations. And you can actually see that, well, we would have to take about 7 times 10 to the power 7 times more function evaluations than here in 100,000. So that's really out of the question. And this really shows this first order behavior of both left and right rectangle rule. Let's take a look at midpoints. Midpoint is the integration method from which I showed you that it should be second order. So for a midpoint with one function evaluation, we find that the error is equal to 3.23. If we take 10 function evaluations, well, this is already 2 orders of magnitude smaller. So the error has decreased with a factor of 100. Again, from here to here, we multiply n with 10. So that means dividing h by 10. And the error is divided by a factor of 100 again. So this clearly shows nicely second order behavior. Same goes for the trapezoid rule. So also from here to here, we have a decrease in the error of a factor of 100. So that's again second order behavior. So note that in order to get actually a completely accurate solution up to 10 decimals, we still have to take really a lot of function evaluations. So although second order is a lot better than first order, it's still not super desirable, let's say. So there's still a lot of room for improvement, especially if we take a look at how the Simpson's methods are doing. So for Simpson's method, well, we see that basically in every step that we take, we're able to reduce the error with a factor of 10,000. And this is very nice because this is fourth order. And so starting from fourth order, I think we can already call this method a high order method. So we see that it is very accurate. So after only, let's say, for 1,000 function evaluations, we can make the error so small that it is negligible. And same goes for the Simpson 3/8 method. So they are both of fourth order. However, I think the star of this slide would be the Gauss quadrature method. And well, for Gauss quadrature, we see that, well, if we have only one subinterval, the error is 3.24, let's say, which is exactly the same as the midpoint rule, because we also saw that, well, Gauss quadrature for only one Gauss point is equivalent to the midpoint rule. But if we take 2 Gauss points, well, we see that already we have about an improvement in the error of a factor of 1,000. If we take 3 Gauss points, again, this is about a factor of 1,000. So let's say 100 to 1,000 of improvement. And this keeps on going. And after only 5 Gauss points, the error has been deemed negligible. So it's very small. Now, this is fundamentally different behavior than what we see in these Newton-Cotes methods. So these Newton-Cotes methods here, every time we multiply n with 10, so this means 10 times more function evaluations that we have to do. So that means that it's 10 times more expensive to compute that the sum, let's say, that is involved in these integration rules. However, for Gauss quadrature, we just added one. So we didn't multiply with 10. No, we just add one Gauss point in there. So one more function evaluation leads to a drastical reduction in the error. So this is a lot, well, this is basically a completely different game that Gauss is playing. So Gauss quadrature is it's much more accurate than either of these Newton-Cotes methods. So that's a bit the point that I'm trying to make here. Now, a detailed analysis of the error in such Gauss methods, that is a bit out of the question. It's a bit out of scope for this course. We did a relatively detailed analysis for each of these methods, especially for midpoint rule, but also the rectangle rule is discussed in the textbook. And you could do the same if you want for Simpson's rule, for example. So as, let's say, a closing statement for this lecture on numerical integration, I would give some general advice as to which method you should use when faced with a numerical integration problem. And based on our analysis of the errors in the previous slide, I would say that Gauss quadrature is extremely accurate and should be your main go-to method when doing numerical integration. In MATLAB, there are the functions integral, which implements a specific Gauss quadrature method, um, which I discussed in the video for section 9.7. But also in the specific video for Gauss quadrature, I showed you this function that allows you to compute the Gauss weights if you want a little bit more control about how many Gauss points you want to use, etc. You can look at the MATLAB demo that I have in the video for section 9.6. The major downside of Gauss quadrature is that this requires you to evaluate the function at the specific special Gauss points. So that's a very, very important prerequisite. In order to use Gauss quadrature, you need to be able to evaluate f at these specific Gauss points. And sometimes that's not possible. So for example, quite often you're faced with the situation that you cannot freely evaluate f wherever you want. And this can be due to many reasons, but for instance, you could have f only as a table where you are given equidistant data points. So equidistant values for x and corresponding function values. And that you still have to do a numerical integration there. So this can be problematic because this completely disallows you to do Gauss quadrature. So in that case, I would say, well, use an accurate composite Newton-Cotes method. And this could be, if it's applicable, Simpson's 1/3 combined with Simpson's 3/8 method, or the midpoint and trapezoid method. And for trapezoid, there is this easy function traps, which I also discussed in the video for section 9.7, which allows you to easily compute the integral approximation using the trapezoid method from a set of data points.